After over a century of debate over the age of the universe, we finally know its age, 13.8 billion years. But despite how confident we really are in that answer, there are always a number of challenges to this claim. Most recently, James Webb Space Telescope, or JWST, discoveries of surprisingly massive galaxies dating back to only 325 million years after the Big Bang have driven one cosmologist to a radical new theory that could shatter the long-held notion of the universe's age. The new shocking theory states that the universe is actually 26.7 billion years old, or twice as old as it is generally accepted. This not only sparked a fierce new debate about the age of the universe, but also recalled one of the conundrums that left scientists scratching their heads. If the universe is only 13.8 billion years old, how can it be 92 billion light-years wide? Even if we accept to replace 13.8 with 26.7 billion years, it is still a big difference when putting the age and size of the universe side by side, and inconsistency between the age and diameter of the universe still exists. How can the universe be so vast in just all these years? The answer will be exposed in today's episode of Eyes 200M. One of the laws of physics that gets drilled into us is this: there's a speed limit to the universe, called the speed of light, and absolutely nothing can travel faster than that. If you're a completely massless entity, like a photon or a gluon, you absolutely must move at the speed of light, as no other speed is possible. If you have a positive, non-zero mass, however, you can only approach but never reach the speed of light. You must always travel slower than it. Therefore, it stands to reason, if something emits light at any point, that light can only travel directly away from the source that emitted it. After 1 second, the light will be 29,792.458 kilometers away from the source, 1 light second. After 1 year, the light will be 9.46 trillion kilometers away from the source, 1 light year. And after 1 billion years, the light will be 1 billion light years away from the location where it was emitted. This type of calculation is sensible, straightforward, and intuitive. Under the laws of special relativity, it's absolutely correct. However, our universe is not governed by special relativity, but by something more. The analysis we just covered only applies if space has two specific properties that we know it does not actually possess. For starters, space would need to be flat, like a three-dimensional Euclidean grid. Flatness can be defined for any general space, and the way you can tell whether your space is flat or not is by picking 3 points and connecting them by drawing 3 lines to make a triangle. You then add up the 3 interior angles of the triangle that you just drew and compare the results to what you would get if you simply drew a triangle on a flat piece of paper, or 180 degrees. However, not all pieces of paper are flat, where the angles add up to 180 degrees, and not every instance of space is either. If you drew a triangle on a globe, you'd find that the interior angles always summed up to more than 180 degrees, with larger triangles resulting in greater departures from 180 degrees. Similarly, if you drew a triangle on a horse saddle, you'd find that the interior angles always summed up to less than 180 degrees. The universe is not like a piece of paper. Because of the presence of matter and energy, the fabric of space gets curved depending on how matter and energy, and especially mass, is distributed. But even more importantly than being curved, the fabric of space is not static. This is more than just the intuitive. Okay, masses move around and masses determine how space is curved, so therefore the spatial curvature changes. That statement is true, but there is something much more profound happening. Under the laws of Einstein's general relativity, which is our theory of gravity, a universe filled with matter and energy cannot be static and stable. If you start a universe in a static state and simply allow it to gravitate over time, it will not remain static. Instead, it will collapse, and in short order, your entire universe will come to an end, forming an inevitable black hole. This clearly hasn't happened to our universe, and there is an excellent reason why. If you uniformly fill your universe with matter and energy, it must either expand or contract. The distance between any two well-separated points will change over time. We have no way of knowing, first from principles, which one of these would wind up describing our universe. The same way you cannot know whether the square root of 4 is +2 or -2. Both expansions and contraction are mathematically allowable solutions for our universe. But we have to measure the universe itself to find out which one is occurring. The key observations for solving this problem were made all the way back in the 1910s and 1920s. In fact, it was a combination of 3 sets of observations that led to a solution for this puzzle. Number 1, Henrietta Leavitt's work on Cepheid variable stars, which relate the time period it takes for such a star to go from maximum to minimum brightness, and back again to the intrinsic brightness of the star itself. Number 2, Vesto Slipher's work on redshift, in which he measured a significant number of the spirals and ellipticals in the sky and determined, from the shift of their emission and absorption lines, how quickly they appeared to be moving toward or away from us. And thirdly, Edwin Hubble's work, assisted by Milton Hummondson, in which individual Cepheid stars were measured in those spirals and ellipticals. With those combining properties, we could determine both the distance to a spiral or elliptical galaxy, as well as the inferred motion of those galaxies. When that data was put together, both initially and in modern times, the result is unambiguous. The farther away an object is, the more light its redshift and the faster it appears to be receding from us. In other words, the universe must be expanding. This has major implications for the idea of a static universe. If the universe were static, then the amount of time it took light to travel a certain distance from the emitting source to the observer that absorbed it would be exactly equal to the conversion from years to light years. Because light must travel at the speed of light, the light arriving at our eyes today from an object 1 light year away took a year to journey to us. An object 1 million light years away took 1 million years to journey to us. An object 10 billion light years away took 10 billion light years to journey to us, and so on. This means that if our universe is only 13.8 billion years old, which is the amount of time elapsed since the Big Bang, then the most distant light we could possibly see must be arriving to us after a journey of 13.8 billion years, and hence that light must have traveled 13.8 billion years. This is consistent with the space-time tool known as a light cone, where everything inside the cone is connected to us, meaning a signal from it could affect us, or a signal from us could affect it. But everything outside the cone is disconnected, meaning no signals can be exchanged. But the scenario we live in is in an expanding universe, and that changes everything. Instead of viewing space like a grid with objects strewn about, the best way to imagine it is as a loaf of dough in some zero-gravity oven, where the dough is filled with raisins. Each individual raisin represents a gravitational bound structure in the universe, a star cluster, a galaxy, a group of galaxies, or something even larger. Each raisin also isn't bound to any other raisins. They are far enough apart that gravity will not bring them together, even given an infinite amount of time. Why? Because the dough is rising, and that dough represents the fabric of space-time. As time goes by, the universe expands, and distant raisins, galaxies, appear to move away from one another. This is the key point that's so hard for most people to understand. The expansion of the universe isn't about speed. The universe doesn't expand at the speed of light, the speed of sound, or any other speed. If you were to look at a raisin that's close by you, it would appear to move away from you relatively slowly, and at a light signal sent from it to you would only take a short amount of time to get there. But if you were to look at a raisin that was much farther away, it would appear to recede much more quickly. A light signal sent from it to you would take a very long time to get there. The reason is because the expansion of the universe depends on how far away an object is from you. It's not a speed, it's a speed per unit distance. This is why when we talk about the measured expansion rate of the universe, what we sometimes call the Hubble constant, it comes along with such weird foreign values, something like greater than 70 kilometers per second per megaparsecs. This tells us that for every megaparsec, MPC, or about 3.26 million light years, a galaxy is distant from any other galaxy, it appears to recede at 70 kilometers per second. So, if an object is presently 100 megaparsecs away from us, it appears to move away at 7,000 kilometers per second. If an object is 4,300 megaparsecs away from us, it appears to move away at around 300,000 kilometers per second, or the speed of light. And if an object is 14,100 megaparsecs away from us, it appears to move away at around 980,000 kilometers per second, which is a crazy large number. But, as I keep saying, and something you may be glossing over, it appears that these objects are moving away from us at these speeds. In reality, the objects themselves aren't moving, just like the raisins aren't moving relative to the dough that they're in. Instead, what's happening is that the fabric of space-time itself is expanding, and the light coming from these objects is getting stretched to longer, redder wavelengths as the universe expands. This is why we talk about the redshift of distant objects, because their light gets stretched as the fabric of the universe expands. It's the matter and energy density of the universe that determines how quickly the universe expands, and we have to add up all the different types of energy, including neutrinos, radiation, dark matter, and dark energy, to get the right answer. Today, there's light arriving at our eyes from all sorts of different objects at all sorts of different distances. The objects that are 13.8 billion light years away from us now were much closer in the distant past. When they first emitted the light that's reaching us today, this occurred at a time that was already billions of years ago. That galaxy might be 13.8 billion light years away right now, but the light didn't need to travel for 13.8 billion years to reach us. It traveled a shorter distance and for a shorter amount of time. In fact, we can see objects that are farther away than 13.8 billion light years today, all because of the fact that the fabric of the universe itself is expanding. So, what do we do if we want to know how big the observable universe is? We need to ask the following question. Given all we know about the expanding universe, and what the different amounts of all the different types of energy that are in it are, how far away would an object be today if its light were only, just now, arriving after a journey of 13.8 billion years? If you do the math, you will get an incredible answer, 46 billion light years, or 46.1 billion light years if you want to be even more precise. If our universe had more dark energy and less matter, the answer would be slightly larger. If the universe had more matter and less dark energy, the answer would be slightly smaller. But that's how we get to the edge of the observable universe. This doesn't mean we can reach everything in the part of the universe we can see. The most distant parts of the universe are only visible during the earliest stages. In fact, everything that's more distant than about 4,300 megaparsecs or 14 billion light years today is at the limit of how far we can reach at the speed of light. The object more distant than that can still be seen by us, but only as they were in the past. Similarly, they can only see us as we were in our past. Someone more distant than 14 billion light-years from us, even with an infinitely powerful telescope, could never observe human civilization as it is on Earth today. The fact that we can see the universe we do tells us that it must be expanding, a fantastic match of theory and observation. It also tells us that we can extrapolate back in time to as early a stage as we want and find all sorts of interesting milestones that happened as far as the size of the universe is concerned compared with its age. When the universe was 1,000,000 years old, its edge was already some 100 million light-years away. When it was just a year old, we could see for nearly 100,000 light-years. When it was just a millisecond old, we could already see for a light-year in all directions. And today, 13.8 billion years after the Big Bang, the farthest thing we could possibly see, corresponding to the light emitted at the first moment of the Big Bang, is 46.1 billion light-years distant. Given the contents of our universe, it couldn't have turned out any other way. Amazingly, a new study was released recently challenging the long-held notion of the age of the universe. Picture this. Our universe is not the spry 13.7 billion-year-old entity that we once believed it to be. Instead, it could be a grand 26.7 billion years old. This finding, according to a new study by Rajendra Gupta, adjunct professor of physics at the University of Ottawa, fundamentally changes our understanding of the universe and may solve the puzzle of the, quote, impossible early galaxy problem. The James Webb Space Telescope has discovered early galaxies that seem to be far too advanced for their age. These galaxies were around just 300 million years after the Big Bang, but had the mass and maturity typically seen in galaxies billions of years old. What's more, they're much smaller than we'd expected, adding another piece to the puzzle. This is where Fritz Zwicky's tired light theory comes into play. According to this theory, the redshift we see might not be due to galaxies moving away from us. Instead, it might be because light loses energy as it travels across the universe. For a long time, this theory conflicted with what we saw in the universe. But according to Gupta, if we let this theory coexist with an expanding universe, we can reinterpret the redshift as a combination of both these phenomena. But Gupta didn't stop there. He also introduced a new idea based on physicist Paul Dirac's hypothesis about coupling constants. These are fundamental physical rules that control how particles interact. According to Dirac, these constants might have changed over time. If we let these constants evolve, then the time for early galaxies to form extends from a few 100 million years to several billion years. That could explain why the galaxies we see are so advanced for their age. Finally, Gupta challenges the traditional interpretation of the cosmological constant. This represents dark energy pushing the universe to expand faster. Instead, he proposes a new constant that accounts for the evolving coupling constants. This change could help us understand why the early galaxies were smaller than expected. It also offers a more accurate picture of the universe. The universe might be much older than we thought, and that could shed light on some of the biggest mysteries.
Let's discover something new today. Here's something that we have limited understanding of. Let's improve on that. And in so doing, we deepen our understanding of how things work in the universe. If you have an idea about something, then you test it multiple ways and get other people to test it. And if the tests give you consistent results, you have a new understanding of the universe.
Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.